So hi everybody, thanks for joining us. Sorry, I woke up sick this morning, thanks to my kids. Ooh. I'm glad I'm not leading that session. That would be horrible for everybody. So today we're going to talk about lava flows and lava flow models on Victor. And so this session will be led by Einat Lev, who is a PI from the Victor project at Columbia University. And so just wanted to say thanks for all those who already put their Tephra 2 homework assignment on the Padlet. Looks great, and yeah, I also saw that some of you even changed the area of interest to your volcano. That's great. That's exactly what we're looking for. So keep doing that. That's makes us really happy, and let us know if you have any questions, anything. I thought there was a question about how to save a file, so I answer on the Slack channel, but maybe Sam or Einat, you guys can show everybody how to use the save fig command at some point to save a file on your directory. But yeah, if you have any other questions like that, don't hesitate to let us know. Einat?
Yeah, hi. Hi, everybody. Thanks for coming to today's session where we'll talk about lava flows and also how we can work on modeling lava flows on Victor. So this is probably a crowd I don't need to explain to, but lava flows are really, really important. And while they don't usually directly kill people, they cause huge damage. So for example, this is a satellite image taken before the 2018 eruption in Kilauea in Hawaii, where this is a subdivision called Vacation Land. This is an old volcanic cone from the 1950s eruption. And then this is how it looked after the 2018 eruption. So terrible devastation. And then this is Leilani Estate, a little bit further up the eruption flow channel path, and this is where the actual vent was. So this is before the 2018 eruption, and this is after. So obviously huge devastation. This site here is a geothermal power plant that was a very big risk during the eruption. Luckily, it was a little bit elevated, so the flows just engulfed it from different directions, but it required removing a lot of toxic materials and gas tanks and things like that, because if the lava had reached those, that would be an even worse disaster. This is the picture of that power plant with, you see how close the flow got to the areas of the critical facilities. This is picture of the power line poles and how they were trying to insulate them from the lava to kind of slow down how quickly they would collapse and cut power. This is lava flow damage from the 2021 eruption in Cumbavieja, La Palma in Spain. You see this house, this road, obviously all gone. This is going to be a video where you can kind of see some of that damage. Houses burn on fire. So once this lava flow was deposited and cut this road, it took months before it was cold enough inside that they could dig through and reopen this road. I'm sure you've all seen some of these beautiful photos also from Iceland, also in 2021. This was the main event, and in that case, there was not a lot of damage during the beginning of the eruption. There was more in the following phases of it. So it became a tourist attraction, and you can see all these visitors who came very, very close to the lava because it's fascinating. I mean, once you see it, it's just mind-blowing. But the Icelandics were also trying to block the path of the lava flows using earthen berms that they were constructing. So these are the bulldozers. They were trying to stop it. This is when the lava was just kind of coming close to that berm. But eventually it overtopped it. And then it came down that valley. You can see here as it was June 9th. And then it just got overtopped all the levees they put here and here and here and filled out that valley because there's only so much you can stop a lava flow. So this is obviously the damage and maybe some of the mitigation efforts that people try to use for lava flows. But for all of these, to prepare for the possible damages and to come up with effective mitigation efforts requires modeling. So this is, we'll talk a little bit about the goals of modeling and the types of modeling, and then we'll try some modeling of lava flows ourselves using Victor. So the goals of modeling lava flows can be the short-term forecasting where you're trying to answer the question of where will this specific lava will go, and also how quickly will it get there. It's a different civil defense response if it's the lava will get to a place in a day or in 2 weeks. For example, if you need to close a road, if you need to evacuate a community. Then there is modeling for the purpose of hazard assessment. Where will some future lava go? Or how hot, how dense, how fast will that lava be? So for that case, you need to maybe do some statistics of where that lava might be coming from. Where would the vent be located? What would the flux be? How much is coming out per minute? So there's a lot of uncertainty that comes into the modeling there. Well, in the short term, you kind of already know some of that. Then there is modeling with the purpose of interpreting deposits. You see an old flow. There's maybe no witnesses for it, no recording. So trying to understand what was the effusion rate, what was the lava like, and that goes into bigger scale calculations like what is the magmatic supply rate to a region, what is the overall thermal evolution of a region. And then there's modeling of lava flows with trying to understand fundamental processes. So how do landscape or rheology or pulsing or time dependence of effusion, how is the cooling processes, how all these kind of physical processes influence lava flows. So these go back into physics where perhaps a researcher would span a parameter space of some properties or some conditions to get an intuition into how these processes affect lava flows in general. And for all of these types of modeling, we always want to ask ourselves, how uncertain are these assessments? Even if we know what the vent is, what the flux is, what the lava is like, how uncertain are we about where it's going to go? Maybe there's uncertainty in the topography data. Maybe there's uncertainty in the properties of the lava because we can't directly measure it, and so on. There's also a way of categorizing lava flow models by the type of math that they do. There's a category that would be called physics-based, where there's a solution of usually a numerical solution of differential equations that solve for energy, momentum, and volume conservation. And then there's models that rely on rules. We stop this flow when it's 5 kilometers long because that's what we know the maximum length of flow has been in this volcano. Maybe we stop this effusion, this dispersion by a certain thickness because we know flows in this volcano never go above that thickness, and so on. Another way to categorize models is deterministic, where we ask where, when, and how will the lava disperse. And then there's probabilistic, where we ask the same questions, but also look at how likely. And these interact, these two categories kind of interchange because in a deterministic model, where you solve the model, you run the model with certain parameters, it always gives you the same result. It can be run in a probabilistic framework if you have enough computing power, where, for example, you draw the location of the vent randomly, or you draw the flux randomly from some distribution. So it's not a clear cut. This is deterministic, this is probabilistic. You can always run in a probabilistic framework in a deterministic model. Models also vary in complexity of the physics considered and the numerics. The simplest models for lava flow only take as input the topography and the location of the vent, and then they just follow the path of steepest descent. Examples for some of these codes are downflow and multiflow. The advantage is they're really, really fast. Sometimes they would maybe follow the path of steepest descent with a little bit of noise to give you an uncertainty of where the lava would go. A level above that in complexity is codes that are based on just kind of a rule-based distribution of a lava from a location to the next location. This can be done with a cellular automata method. We'll talk about that in a minute, or lobes, where one lobe gives birth to another lobe or multiple lobes based on some probability and some rules. These two categories of models usually just answer the question of where. They don't have physics, so they don't usually tell you how quickly the lava would get there to a place, or what the properties would be, how hot would it be, what the momentum and things like that, which is important, for example, for engineering mitigation efforts. Next level up is depth average models, where we're already solving the partial differential equations. To make it a little faster, we use a depth average formulation, assuming there's no variation in the vertical direction of the flow, because usually flows are much longer than they are thick. So these assumptions usually hold for lava flows. Examples for some of these codes, PyFlogo, which is one-dimensional, VolcFlow, IMAX Lava, and Lava 2D. And then if you really want to kind of like dig into the physics of the problem and look at the fundamental process, then is where you can use a fully three-dimensional models that solve the equations without any of these kind of relaxing assumptions. Usually these are based on some existing numerical packages, finite elements tools, or finite volume tools that are used in other fields like OpenFOAM, Fluent, COMSOL, Flow3D, and things like that. So let's just start looking at some of these models that actually are already available for you to use on Victor. So as I said, this model Downflow was developed a long time ago. Its basic steps is to take a DEM, put a vent somewhere, and then for n iteration that you get to decide the number, modify the elevation at each DEM point by some random value, plus minus delta H. You get to decide that too. And then trace the steepest descent path from the vent through the DEM. It's an option. You can end the trace at a given length. Maybe you say, I know there's not going to be flows that are more than 2 kilometers. And then you get a summary of the results in the form of probability of inundation for each grid point. So get something like a heat map where the reds are cells that are almost always were inundated, and orange or yellows were not as frequently inundated by the simulation. This is an example test case that was published by this group where they looked at the 2014-2015 eruption of Fogo volcano. And you can see the model spread a little bit more than the actual eruption itself. So, but it did capture kind of the higher likelihood did capture the places that did get inundated. Downflow exists on Victor. This is just an example run notebook that we have using the Momotombo 2015-2016 eruption. Here I compared the influence of that DH variable. If I made DH 2 meters, then the change of the DEM was small. So then the path could kind of go lots of different places. If I made it 10 meters, it confined the flow in a lot of places, and kind of only the steepest part were participating. Downflow, because it is so fast, it's often used to create hazard maps where there's a probability of an eruption to occur in a given time period, y years, and assuming some distribution of vent openings. So, and then you multiply that with the probability of inundation for each of these conditions. So that can tell you kind of a bit like more regional distribution of hazard for a region. I think this is Etna, probably. And to do something like that, you need to run the model many, many times, which means you want to have a model that runs really, really fast. So something like Downflow, which doesn't solve any equation, just run the path, is good for that. The next class up, cellular automata models they're popular in volcanology because they're also very fast and they're very simple. You can kind of understand fairly intuitively what's happening. Have a cell with a thickness, and then based on the slope to the cells around it, that's how you distribute the thickness and temperature. So, for example, this is an animation of a cellular automata code called Molasses. And it starts in the middle and then it spreads. This is the overall lava thickness. And it tracks how much volume we've already put in, how much is spreading. The simulation, the parameter that Molasses usually take is what is the nominal thickness we're trying to get to. So it basically takes that overall thickness and spread it until it runs out of the total volume that we tell it that has erupted. So there's no time dependence per se. There's some other parameter called pulse that can kind of serve as a time dependence, but not usually. But that kind of shows you what's happening, and to make it a round circle rather than just kind of an edged square, there's some kind of randomness that's entered into the calculation. Like I said, for Molasses, you want to provide a DEM, the location of the vent, the total eruptive volume, a pulse volume, so how much is in each pulse, and then the average final flow thickness. This is a flow chart where you can kind of see how it goes through, then it goes through and distribute until the end where you get the output either in ASCII or GeoTIFF. Here are Molasses test cases, for example, Tolbacic 2012-2013 eruption, where they looked at the model sensitivity to different parameters by looking at the fit between the simulated flow footprint and the actual lava footprint. There's different ways to assess the quality of the fit between a model and the observations that we have also tools for that in on Victor. This is Molasses run for that 2021 eruption in Iceland, Fagradalsfjall. So I wanted to start with an activity now that you all will log into your Victor accounts and try using this very fast model on your account. So here are instructions for you. So log into Victor and then go ahead and follow these instructions. So how about we take 5 to 10 minutes. It runs pretty quickly. So I'll try to be quiet, not to bother you. But if you have any questions, please put them in the chat. Sam, Sophia, and me will try to help you. At the end, please put your beautiful results in the Padlet. The number for Molasses might have changed since I made the slide, so check that you actually pick the one for Molasses. Do you have a result?
Yeah.
Okay, so the easiest way to copy that is to right-click on the map and then open it in a new tab.
I think with Mac you have to do like a double click on it. I'm not familiar with Mac, but I think you have to like.
Yeah, it's a command click or something.
Because on Windows it's like Shift and then right click, but I think on Mac it's like a double tap or something like that. I don't know if there's on other Mac users.
Yeah, it might be like a command click or control click.
It's still Shift right click.
A Shift right click? Okay.
Yeah, Shift right click will still let you copy the figure.
Oh,
yes, I did it like that and it works.
Oh, great. Thanks, Ron.
Yeah, running cells should not take a while because once you have the machine up, it should be okay. So if the cell is stalling, you might want to restart the notebook. There's a little I don't know what to call it. There's a little restart button at the top of the notebook. So if your notebook seems to be kind of stalled or not running anything in the cells, just restart it, and that should kind of get it running along properly again. And Rosario was also helpful just now saying that Molasses is 13, not 10, because for better or for worse, we constantly add models to the setup command. So,
right. For the sake of time, everyone can continue to do it on their own free time. I'm gonna keep going because there's so many other models that we can talk about. So one of the kind of popular tools that evolved some maybe 10 years ago is a tool that is a plugin to QGIS. It works by looking at a dispersal probability. So in a way, it's kind of similar to downflow and has sort of a built-in mechanism to overcome small pits with that. And then they have kind of a quantified, kind of like an empirical-ish or an analytical reduced probability with distance to account for the cooling of the lava. So based on some distance from the vent, they change the probability of dispersal. And there's a way to limit the flow length as an input parameter, or you can calculate it through a calculation of cooling by solving an actual cooling equation using the Flogo model, which is built in. We'll get to that. These are some test cases for Etna and Iragorgo from the original paper. You can compare the actual observed flow footprint in the black line and the probability of inundation in the orange color scheme. Here are instructions. We're not going to do it right now, but the instructions of how to install QLava for your Victor profile. So you would open the Victor graphical desktop through the launcher, it's that letter D, open QGIS. And in there, under plugins, choose manage plugins, install from zip file. And then we have the zip file for QLava under shared models QLava, so you don't have to go looking for it. And then they can just add that plugin to your QGIS installation, so that then you can provide it a DEM, provide it location of the event, and all these different parameters it's asking for. It has a nice kind of GUI. The next model that has actually been used extensively during the eruptions in Iceland by the Icelandic Met Office to forecast where the lava would go. Then it's called Mr. Lava Loba. Here's the reference. And it, rather than spreading from grid cell to grid cell, they keep a database of lobes. So it can have an initial or a mother lobe. And then there's deterministic, kind of a probabilistic rules of how to make the daughter lobe. So there's a distribution of where that, the direction is based on the slope of the terrain. And then there's a probability around it of which direction exactly it would go. And you can make that distribution wide or narrow as you wish. And then there is some other parameter of how much volume would get dispersed. So first you got to set a preliminary direction, perturb the direction to reflect the distribution, and then add some other parameter to make that happen. Here is a sensitivity of the model to the kind of two main input kind of knobs that you can twist. There's one called lobe exponent, that if you vary that, everything else kept the same, would make the resulting flow thicker and shorter. And then there is the alpha parameter, which works to reduce the flow width. So this is a low parameter. If you have a high parameter, 0.75, it'll kind of focus. So it can take like in a camera where you change your focus, or on a lens. Here are some test cases for Mr. Lava Loba. This is Kilauea 2014-15, where it kind of overshot, but the main thickness was confined to where the actual observed flow footprint was, the blue lines, and then it did really well on the Etna 2001 flow, which a lot of models use as a test case. One of the reasons is that it's pretty steep and a very nicely confined channel that is fairly easy to reproduce. So you say, hey, look, I did really well on the Etna 2001. You want to ask, yes, but how did you do on other cases? Because that's kind of like an easy test for lava flow models, just so keep in mind. Again, Mr. Lava Loba for Fagradalsfjord look a little different than what we saw for molasses. And the next activity, if you want to run Mr. Lava Loba on Victor, I see that it's getting kind of late. We only have an hour, so I want to give this to you as an assignment if you want to do it later. Also, put your results in the Padlet because we really want to see how everyone's doing. Okay, so these models that we've looked at so far only looked at where would the lava go. Now, what we also want to see is how quickly would it get there? How fast will the lava travel? So to know that, we need to know what the rheology is, or the viscosity. One important equation that you'll see sometimes in lava flows is the Jeffreys equation, which for a Newtonian fluid, which relates stress and strain linearly, the maximum velocity of the flow is equals to the density, gravity, the depth square, and the sine of the slope, and then divided by the bulk viscosity. So higher viscosity, slower flow. smaller density, for example, if it's very, very vesicular, also slower flow. So different parameters go into that. There are equations for flow velocity, also for Bingham fluid, which is a Newtonian fluid that has to overcome a yield stress before it starts moving, and a Herschel-Bulkley fluid, which is like Bingham, but has a yield stress, but it also has a nonlinear relationship between the stress and the strain rate. And lavas have often been modeled as Herschel-Bulkley fluids because of particles or crystals and bubbles in them. There's different depth averaged models that solve for flow velocity and temperature evolution as well, because temperature is an important control over lava viscosity. So the one-dimensional Flogo, or now PyFlogo, because it's been converted to Python by Chevreul, VolcFlow, IMAX Lava, and Lava 2D, which we have on Victor, all of those. Specifically, let's go to details. Flogo, PyFlogo is 1D. You give it a track of topography, so like a distance and slope as input, and then give it some initial channel width and thickness, temperature, crystallinity, and composition to calculate viscosity. Then it provides as output a long track evolution of velocity, width, thickness, crystallinity, viscosity, temperature, and where would the lava stop? Where would it develop? And then there's a criteria for stop, which is when the velocity becomes too small. So like 10 to minus 6 or something, like I said, stopping criteria. Here are some examples of the outputs from Flogo for 3 different eruptions. That it gives distance and then the overall width, the core temperature, and the mean velocity as it progresses. And these 3 cases were used because there's actually observations. So these red dots are field data, and you can kind of make your own judgment about the quality of the fit. PyFlogo exists on Victor, and we'll be happy to work with you if you want to use it for your own research. One kind of fun way to use PyFlogo is in statistical. For example, if you use downflow to look at where the likelihood of the lava is to go, and then extract those terrain paths as input to Flogo to understand, okay, this is maybe the most likely path that downflow gave me. I can extract that profile of slope, put it to Flogo, and see how fast or how far it would go along those paths. Another is to, if you for example, if you have a known path, for example, from a fossilized flow from old times or from another planet, and then you can explore the sensitivity to input parameters and see which one actually gives you the observed length. So if I want to know how hot the eruption was or how thick it was in the beginning of an eruption that no one witnessed, then I can use Flogo, see how I can match the observed flow length. Move on to VolcFlow, is a popular depth average flow model that was initially for PDCs and landslides, but then the temperature field got added. It's a closed MATLAB executable, so we don't really promote it on Victor, but it exists as an executable. Similar, yet open source code that solves the equations of conservation of mass, momentum, and energy through temperature is IMAX Lava. Again, it's a depth average, so it assumes no variation on the vertical axis. IMAX lava example provided in the paper is, again, the Pico de Fuego eruption. And you see that's the observations. And what cool, remember that we saw Pico de Fuego already, where we already just saw the footprint match. But now with a time-dependent model like IMAX, you can look at the temporal evolution of when would that lava actually get to different places. And those different places may be a village, or in Fogo, these were actually wine cellars and vineyards. So you can get the temporal evolution, and then you can also explore the sensitivity to different parameters like the yield stress, the reference viscosity, the grid size, temperature dependence of the viscosity, and so on. Here is just an example I ran on Victor for IMAX lava for the Idaho National Lab. It's a big nuclear facility in Idaho that is on a very active volcanic region. So they're concerned about inundation by lava flows. So, for example, started an eruption here from this small vent. This is after 1 day. This is after 1 week, 2 weeks. But you see, this is also giving me the flow temperature, which is very important if you're trying to protect a nuclear reactor. Here are instructions for running IMAX on Victor, and you are very well invited to try it after class or your free time to run through the steps and see the results. I'm posted on Padlet if you want. Last on this category is Lava 2D, which is depth average, but it also makes some assumptions on the temperature profile inside the flow and the profile of velocity, assuming some sort of a plug flow in with depth. So that is still depth average, so it's still relatively fast. Compared to the full 3D kind of finite elements, finite volumes code, but it's not a uniform. Lava 2D was tested during development on these lava flow experiments that were done at Syracuse University with the lava flow facility. So there's a model and observations. So where there's very good control and known thickness and width and temperature and rheology and everything. So it was a really good benchmark case. Here's an example of Lava 2D on one of the kiloware flows. I can't remember which one. Again, here are instructions for Lava 2D. Same instructions as they always are. Victor setup, get the folder, get the notebook, run the steps, and play with it as you like. Just a tad bit about computational fluid dynamics kind of models that have been used to model lava flows, mostly for kind of like researching specific processes, like the impact of geometry of the channel, the impact of the crust, things like that. So there's finite elements codes like Fluent, COMSOL, Elmer, and GetFEM, finite volume code like Flow3D and OpenFOAM, SMAC method used in LavaSim, and particle hydrodynamics code used in GPU-SPH. We don't have any of those right now. We're working on getting a GetFEM based code on Victor. Now, the last thing I want to talk about is how we assess models. There's so many different kinds. So what do you need to ask yourself, and how do you know which one's good, which one's not so good, which one's better fit for your goals? One activity is called benchmarking, which compares the performance of a model on a specific known solution. That can be a field observation, an analytical solution, a lab experiment. Way is to compare models to each other in a model intercomparison framework. Here, for example, is some analytical solution for a dam break or an experiment solution for a dam break. So if you put a dam break simulation case in your model, you want it to fit these node solutions. If you look at a known field case, then you would want to compare the quality of the fit to the footprint. And to do that, one calculation one could do is the Jaccard similarity index, where you look at the kind of A intersection with B. So A, say, is the model, and B is the observation. So the intersection is the true positives. And then you want to you look at the false positives and the false negatives, which are these two areas on the sides, and you want the green to be the largest compared to the blue and red. So that's the index. And then there's other ways of calculating this fit with different ratios. We saw the similarity index earlier, which only had B in the bottom. Then there's a whole package of model assessment functions that Sylvain student Franco developed. It's called BAM for assessing of models. And we have some of this functionality already implemented in the victor.py library. Another way of comparing our models to observations or to each other is, rather than footprint, to look at the branching. So there's a way to calculate the number of internal and external boundary contours in a flow. And for example, if it's just one kind of snake, then it's a low branching index. But if you have many kind of like tentacles, then you have a high index. So you can calculate your index for the observed flow and the model result and see how they compare. For example, these are this is a study on the Mauna Loa 1984 flow, where they looked at the relationship between slope and branching index, and the relationship between branching index and flow width. So that's, for example, a data set that one can use to test a model. Then there was a couple of papers about 10 years ago that defined set models, benchmark tests for lava flow models. Simplest was the dam break, and then going to a point source on an inclined plane, which is kind of like a very simple lava flow situation. Here's, for example, solutions from IMAX lava and other models to have a spreading drop or an inclined plane and a dam break. Here are some experimental results that were used in that benchmark paper to compare different models. So like all these different tests have been explored and defined. So if you use a model, you want to ask, how well is it doing on these different tests? For example, this is a test where the lava flow at Syracuse was going against an obstacle. So one of the things I wanted to say about the benchmarks is now we have developed, by we and Sam developed notebooks that compare different lava flow models on Vector for different benchmark tests. So there is a test for an inclined plane, a test for a spreading point source on a flat plane, the case with an obstacle where you can change the shape and the slope and everything, and a natural example test case using Mauna Loa 2022. So yeah, we said that stochastic models usually look at matching the footprint, while physics-based models look at matching lava velocities. For example, this is a vault flow simulation of the Cumbre Vieja eruption, and it gives you velocities that then you can compare with observed velocities. This is an IMAX run of the same eruption with kind of the channelized flow. You can see has the highest velocities going all the way down to the ocean. So we don't have time to look at the notebooks of the benchmarking, but they exist, and you can get them installed if you run Victor Benchmark rather than Victor Setup. That would copy all the models and all the notebooks into your folder, and you can start looking at them. Then there is a ton more information about lava flows on these special volumes. Geological Society of copy that looks at detecting, modeling, and responding to effusive eruptions. Then there's Annals of Geophysics, observation and modeling of lava flows. So I guess to summarize, there's many factors that impact where lava would go, mainly the fusion rate, the topography, and the lava properties. There's many different models available. There's lots of them on Victor because I'm obsessed with lava flows, and they have a wide range of levels of complexity, which also translate to speed. As a user, you should consider what is your goal, what are you trying to get, and select the appropriate tool. Do you want something that's kind of fast but maybe less accurate, or something that gives you like really focus on the process? And then there's benchmarks and intercomparisons, tools that can help users make an informed choice. So this is it for today. Thank you, and being open to questions, and hoping you'll have success with all these tools that are now available for you.
Thanks, Anat.
Thank you.
Is there any questions? Yeah, one.
Hello, thank you, Einat. I'm just curious about if there is, because I don't know if there are some examples of fragility functions to assess the impact that a lava can have in a building. And if so, do you think that is useful? Well, perhaps the word is not useful. Do you think that is worthy to assess the impact in buildings, considering that I have made some examples where the vulnerability is a binary value, is reached or not by the lava, because at the end it's a highly destructive process, as you say. So is it worthy? And if it's so, which parameter? Because for example, in the models you show that usually they have the output is in terms of thickness or temperature or velocity. Which parameter will be useful for this aim?
Yeah, so you're thinking like from the engineering perspective, that came up, for example, in the discussion around the Idaho National Lab. There's a question like, given a wall thickness, how long will it take the heat to go in? And that's codes that don't really exist in the lava flow literature. They exist in engineering, but the lava flow model would need to provide the boundary conditions, right? So you want to run a physics-based lava flow model that will give you arrival time, thickness, and temperature, and then you can provide that to the engineer modeling the wall or the building. It's usually the temperature that is the main thing, not the momentum. Sometimes there can also be kind of a physical kind of plowing over. Haven't seen that much happen with lava to buildings. I've seen that happen to trees that get just like flattened out. Though oftentimes trees also just stand there and then just burn, which if you go to places like Hawaii, you'll see kind of tree molds. So vertical cylinders that are empty because there was a tree before, the lava went around it, now the tree burned, disappeared, you're left with a hole. So it's mostly the temperature and how long will something take to burn or to melt or whatever it is that you're dealing with.
What about dynamic pressure? It's not really something for lava flows, or I know for PDC, that's the primary thing we look for building. It's like, you know, how the dynamic pressure is going to be impacting the building.
Right. So it's a thickness, and if you have something thick and it's above the wall because it's on a slope, that can lead to collapse over time. Okay. It's mostly the weight. So it's not momentum, it's the weight.
Thank you.
Welcome. Thanks for the question.
Anything else? Okay, so I guess you guys can have a try with some of these models and let us know your experience, either with the Slack channel or if you're available during the office hours that's going to start now. You can also stay and then do that during the office hours. And otherwise, we'll meet next week. We're going to talk about progressive density currents. Thank you all, and I'll see you next week.